This is lecture 8A for Calculus 2 on arc length and surface area of a solid of revolution. First, we derive the expression for the arc length, since this expression is then used in the surface area for the solid of revolution. What we're trying to calculate with arc length is the length of a curve traced out by some function f of x between two endpoints, which we're calling x1 and x2. As is typical in calculus, when we have a problem we don't know how to do, we divide it into little sections and make some kind of approximation in each little section of a figure that we do know how to calculate. In this case, we know how to calculate the length of a line. So if here's our figure traced out, I'll kind of trace it out in blue here, and that's the function. Let me get the pen. Okay. So in blue is our function f of x. And what we do is subdivide it into sections, and with each section we approximate it by a line. So this is just a, well, this should have gone the other direction. Okay. Calculate the length of the lines, add them up, and call that the length of the curve. Of course, we chose these lines because we know how to calculate the length of them. Using the Pythagorean theorem, the length along the line is the square root of delta x squared plus delta y squared. All right? We can factor out a delta x, and when we do that, we end up with the length of each section equals delta x times the square root of 1 plus dy over dx squared. dy by dx is just the slope m of the little linear section. Right, we're almost there. We have a few more steps to go to derive this the arc length function and the arc length. Okay, so here we have the slope, which is dy by dx. And now we're going to invoke the mean value theorem. Now, the mean value theorem says that for any function, if you take the average slope, that is the slope of a line connecting the endpoints, that somewhere along the function there is at least one point, which I'm going to call x star, where the derivative at x star is equal to the average slope. So I'll just draw a little picture here to remind you of what we're doing. So here's our coordinate system. Here's our function. All right, I'll draw it like that. Now the red's going to be the average slope. This is going to be the m. So I've taken these two endpoints and drawn a line between them. You see, this is exactly what we did when we made that linear approximation for the arc length function. So this is our little linear approximation to the function here. This is going to be one of the little subintervals. This is m, which is that average slope. The mean value theorem says that somewhere along this curve there's a point, perhaps right here, where the derivative is equal to this average slope m. Doesn't look like much of an m. Whoa, because I didn't have the pen. Okay. So this is m right here, average slope, and somewhere at some x star, the derivative equals m. Now, instead of trying to calculate slopes of little sections, we're now back to looking at the derivative of the function itself, and it was that the function f that we were trying to calculate the arc length for. So this is very handy. And here's our result, and we can substitute this into the expression for the length of each segment. If you remember previously, the length was equal to the square root of 1 plus m squared delta x, and now we can write it's the square root of 1 plus f prime at x star squared, ooh, there's a squared missing here, delta x. Then the length of the whole curve is just adding up all those little lengths. Now we can take the limit. So when we take the limit, Remember we had L, well, I need the pin, sorry. L is equal to this finite sum with a square root of 1 plus f prime at x star squared delta x, and this was for each little section running from n equals, say, 1 to n, the number of subsections that we created. We're taking the limit, by that I mean the limit as delta x goes to 0. The result is a definite integral varying from x1 to x2 of 1 plus the derivative squared dx. You can also express the write the curve as an expression of y, and you get the same, a similar result. But this expression here is the arc length function. There are two more quantities associated with arc length. One is the arc length function, the other is the arc length differential. The arc length function is a more general expression. Instead of calculating the length between endpoints x1 and x2, this is a function giving the length from x1 here to an arbitrary point x. And it's written as s of x. S of x is the definite integral from a fixed beginning point, which I'll call x1, to any other point x along the curve. The expression is the same, 1 plus f prime, and now I have to use tau as a dummy variable of integration because I have x as one of the limits. Okay, here's a summary of these arc length terms. One is the arc length, which is the total length of the path from some starting point, calling x1, to some ending point x2, and it is a definite integral between x1 and x2 of 1 plus the derivative squared. The arc length function is the distance to any intermediate point, or any point along the curve, start from x1 up to some value of x. And I've changed from x to tau as my dummy limit of integration. Same expression, 1 plus f prime squared. The arc length differential can be derived with just a little bit of algebra, and that's done in the written lecture notes. The arc length function is called ds, named ds, and it is just 1 plus f prime squared dx. You can see it right here. Or if you're integrating with respect to y, it's 1 plus some function g of y. Looks like I missed the derivative sign here. It is a derivative g prime squared dy.